Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to look at random processes that pass through zero memory nonlinear systems. Today's video lecture is going to really be comprised of a couple of examples. Linear systems, by their very nature, are not easy to characterize in any closed form systematic manner. When we get into discussing random processes that pass through linear systems, we'll be able to get some closed form results that relate the input to the output and vice versa. For nonlinear systems, we have to do it example by example by example. So today is just going to give you a general flavor for how we might tackle the problem of passing a random process through a nonlinear system. All right. Zero memory nonlinear systems. What are we going to do? I'm going to have some sort of nonlinear system. I'm going to have an input random process, X. I'm going to have an output process, Y, which is a function of X. And my transformation function will depend upon the system. Okay? We are going to, in all cases for this discussion, we're going to assume that my input random process is at least wide-sense stationary. That will also imply that the output is at least wide-sense stationary in this case. So X of t and Y of t are at least wide-sense stationary. All right. Zero memory. Zero memory, I need to get a hyphen in there. That means that my output at time t depends only on the input at time t. Depends on the input only at time t and not upon past or future inputs. All right. Systems whose output don't depend upon past inputs are ones with no memory. Another word is hysteresis. So a system whose output doesn't depend upon past inputs has no memory or hysteresis. Okay? Systems whose output doesn't depend upon future values is said to be causal. All right? So we're going to have causal systems with no memory and no hysteresis. We're also going to assume or ignore all system delay. All right, so we can either assume that my system responds instantaneously to inputs, or we're just going to ignore any system delay. All right? Okay. So, like I said, we're going to just approach this discussion from a couple of examples. Let's look at the first one. My first example is going to be that of a dead zone device. The input-output characteristic for my dead zone device is shown in the upper right-hand corner of this page. What we see is if the input X is above plus C, we have a unity gain at the output. The input equals the output as long as the input is greater than plus C. Likewise, the input equals the output with unity absolute value gain if input X is less than minus C. This might be, for example, a gain characteristic, a unity amplifier gain characteristic for maybe a push-pull type amplifier. A separate transistor or op-amp circuit that amplifies positive going portions of my input, and another amplifier or transistor circuit that amplifies the negative going portions of my input. In those kinds of situations, especially when transistors are involved, when the input gets too small, the transistor simply cuts off and we have no gain of any sort. There's a dead zone in there. Anyway, here's my dead zone characteristic. We're going to assume that my input has a first order probability density function that's zero mean Gaussian. That's a zero mean Gaussian probability density function. The standard deviation is sigma. All right. What we're going to do is we're going to try to find the output. What we want is we're going to find the output probability density function, first order probability density function for y. And you'll notice that in both cases here, in the probability density function for x and the probability density function for y, I'm not including time functionality because I'm going to assume in all cases that my input and output are y-descent stationary. So our goal is to find my output first order probability density function based upon knowledge of the input first order probability density function and my gain characteristic over in the upper right hand corner. The way we're going to do that is by finding the cumulative distribution function first and then taking a derivative. So let's do that. So for y greater than 0, y greater than 0 is this region over here that I've shown in blue. For y greater than 0, my cumulative distribution function equals the probability that y is less than or equal to some unspecified value little y. That equals the probability that x is less than or equal to a value little x, which equals y plus c. And what do I mean by that? Over in the right-hand corner, right here, y equals x minus c is the same thing as x equal y plus c. Okay? So, one more step. This is equal to the cumulative distribution for x evaluated at y plus c. Okay? So the cumulative distribution function for y follows the same functional form as the cumulative distribution function for x if everywhere I substitute x for y plus c. All right. Let's look at what happens for y less than 0. Now for y less than 0, we're looking at this region here. All right? For y less than 0, the cumulative distribution function for y equals the probability that y is less than or equal to some unspecified level. and that is the probability that x is less than y minus c. The reason being that over here, that relationship can be rewritten as x equals y minus c. And this, of course, is then the functional form for the cumulative distribution function for x evaluated at y minus c. Okay? That's that. All right, so now what we're going to do is we're going to take derivatives of these two results for y greater than 0 and y less than 0 and get access to my probability density functions. All right. All right. So for y greater than 0, the probability density function for y equals first derivative, or first partial derivative with respect to y of the cumulative distribution function, and that is so the probability density function for y equals the probability density function for x, the functional form for the probability density function in x, where everywhere I substitute y plus c for x. So this equals 1 over sigma square root of 2 pi e to the minus y plus c quantity squared over 2 sigma squared. Now I have to throw in a step function, u of y. All right, remember, I'm talking about the region for which y is greater than 0. I have to throw in this step function to force this portion of my result to be valid only for y equals 0. However, let's take a look at this. Here is a Gaussian type function. If it was in isolation without this step function in y, this piece would be centered at y equal minus c. So that portion, the Gaussian portion alone of this part of my result would be centered at y equals minus c. It would be shifted to the left a little bit. But I'm only going to consider those values for y positive. All right. Similarly, for y less than 0, I'm going to have this. By exactly analogous steps, I'm going to have my probability density function for y will be 1 over sigma square root of 2 pi e to the minus y minus c quantity squared over 2 sigma squared. And now I have to throw in a u of minus y. All right, so I'm only considering negative y values here. This step function forces me to consider only negative y values. And once again, if I looked at the Gaussian piece of my result in isolation, that portion would be centered at y equals plus c. It would be scooted to the right just a little bit. All right? Okay. So now what we have to do, let's go back and look at our picture just a second. Let's go back over here. There is a region over which y equals exactly 0. I'm showing it here in green. All right? So there is a portion of the range of x for which the output is exactly 0. All right. All right. So what about the range negative c less than or equal to x less than or equal to c, for which So what about that range of x values for which the output equals exactly 0? Let's tackle that on the next page. First of all, recall this. If I have a general Gaussian that looks something like this, and this is the mean value, and that's the standard deviation, and this is some value x naught. This area, that area right there, equals Q, remember that, Q function, evaluated at x naught minus m over sigma. All right, remember that. Now for our case, for our example, the mean is 0. We're talking about a 0 mean Gaussian input. Right? So the probability that my output random process equals 0 exactly equals the probability that my input random process lies between minus c and c, and that is 1 minus 2 times the probability that x is greater than c, and that is 1 minus 2 times the Q function c over sigma. Because once again, remember, we have a 0 mean Gaussian random process. So then, let's go to the next page and summarize all this. In summary, for this particular input-output characteristic with a 0 mean Gaussian input process, we have 1 over we have that part. We have a finite probability of y equaling exactly 0. So we have to throw in our throw in a delta function times the probability that y exactly equals 0. And then we have this, 1 over sigma squared root of 2 pi e to the negative y minus c squared over 2 sigma squared u of minus y for y negative. All right, that's my result. All right, I have 3 pieces to this equation. All right, well, so what's it look like if I plot this out? There's my result. All right, if I plot the output probability density function for my dead zone device, excuse me, assuming that I have a stationary zero mean Gaussian input, this is the output probability density function. You'll notice that I plotted this for sigma equals 1 and c equals a half. That's kind of arbitrary. And remember, the piece of the probability density function that's valid for y negative in the absence of that step function would be centered to the right. Likewise, the portion of my output probability density function that is valid for y positive in the absence of the step function that is included would be centered somewhere over here to the left. That's what that means. Okay? So I'm only interested in a certain portion of those Gaussian functions shifted either to the left or to the right, and I make up for the fact that there is a finite region of input values over which the output is exactly 0 by including this delta function right there. Okay? All right, that is all for that example. And by the way, I should give you this value here. The peak of this delta function right there is about 0.4, 0.4. If you go in and you plug in the values that I've given you, sigma equals 1 and c equals a half, I think you'll find that that delta function is 0.4, roughly. Okay. Let's do my next example. Here's my next example. Sorry about that. This is what I'm going to call a limiter function. Second example is a limiter function. It could also be thought of as a saturated amplifier input-output relationship. All right, you'll notice it's got unity gain when the input is between negative b and plus b. When the input is greater than plus b, the output is limited to plus b. When the input is less than negative b, the output is limited to negative b. The reason I call that a saturated amplifier characteristic is if you've ever built a, say, a non-inverting op-amp amplifier circuit, my output voltages can never be larger than or smaller than the power supplies. So typically when you build an op-amp, you've got a plus voltage supply and you've got a minus voltage supply. The output can never be greater than the positive voltage supply and can never be less than the negative voltage supply. So sometimes it's what we call hitting the rails. If the input gets too large, it saturates, it hits the rail, it hits the more positive supply voltage and limits the output. Anyhow, this is what we've got. Once again, what we want to find is the output probability density function given knowledge of the input probability density function. We're going to assume once again that the probability density function for my input is a zero mean stationary Gaussian. Alright, it's a zero mean Gaussian stationary, at least wide sense stationary input. And what we want to find is the output first order probability density function. And once again, we're going to set up the cumulative distribution function for the output y and take a derivative to get the probability density function. Alright, so we'll look at three regions. First region is for y greater than or equal to b. The cumulative distribution function for y in this region is the probability that y of t is less than or equal to y. And we are looking at this region, y greater than or equal to b. And clearly, based on this input-output characteristic, the likelihood that y, by random process, y will be less than some value greater than b is exactly 1. All right, it'll always be less than plus b. All right. Likewise, for the region y less than minus b, the probability that output random process will have a value less than negative b is exactly 0. We're now looking at that region. Okay? Then, for this region, for negative b less than or equal to y less than or equal to b, the cumulative distribution function for y equals the probability that x is less than or equal to some unspecified level little x, which also happens to equal y, because in this region y equals x, unity gain in that region. And so this just simply equals the functional form for the cumulative distribution function in x, where everywhere I switch x and just plug in y. Okay? All right. Good enough. Now, we take the derivatives of this to find the probability density function. Okay? All right. So, if we So over the range negative b, excuse me, that needs to be a plus b. For the range y equals negative b up to plus b, my probability density function at the output equals the functional form of the input probability density function, where I simply change x to y in all cases. All right? My probability density function in all cases equals 0 for y greater than b and y less than negative b. Okay? However, there is finite probability that y equals plus or minus b. Okay? There is a finite probability that y equals plus or minus b. All right. That probability is this. The probability that y equals plus b by symmetry equals the probability that y equals minus b. That's by symmetry. Okay. This is the probability that x is, greater than or equal to b. And by symmetry, this is also equal to the probability that x is less than or equal to negative b. And by using my Q functions, this is equal to Q of B over sigma. Okay? Q of B over sigma. All right. So let's summarize this. My probability density function for y will equal Q of B over sigma, and I'm going to locate this at negative b. Y delta function of y plus b. That delta function locates this portion of my result at y equals negative b. It's going to be Gaussian. Oops. 1 over sigma square root of 2 pi e to the minus y squared over 2 sigma squared in the region negative b less than or equal to y. I guess I need to make this just less than because I've got delta functions at y equals b. And then another delta function, Q of b over sigma times a delta function y minus c, and this is valid for y equal plus b, and it's 0 everywhere else. All right. All right. So we have finite probability that y equals plus or minus b. And that's shown by use of the delta functions here. We have a Gaussian-like probability density function for the output in the region negative b to plus b. If y is for y values greater than plus b or less than negative b, there is no probability. All right. So then, let's look at the result. Here we go. This is my result. I've got two little delta functions at, well, let me tell you what I've got here. First of all, I assumed that sigma equals 1 and b equals 2 in order to plot this particular result. You'll notice that my function My output probability density function is Gaussian in the region between negative b and plus b. And you'll notice that there is a finite small delta function that sits at plus or minus b. Okay? That's it. That is all I've got for these two examples. Again, just a quick introduction to how random processes might be affected by nonlinear systems. I can't characterize nonlinear systems in closed form in a closed form fashion for all possible systems. We have to approach that on a case-by-case basis. We'll get into linear systems shortly, and we'll be able to get some results for input-output relationships that are valid for all possible linear systems. Anyhow, that's all for today. As usual, if you have any questions, please do contact me at your earliest convenience, and I will answer them as quickly and fully as I am able. Have a nice day. Bye-bye.